Okay, folks, I think I'm going to go ahead and call us to order. It is that time. I'm Eli Sagor with the Sustainable Forest Education Cooperative, talking to you from Green Hall, for those of you online, based up at the Cloquet Forestry Center. And I'm really happy to welcome everyone for the next presentation in a series that's organized by the organization that I am part of, the Sustainable Forest Education Cooperative, along with the University of Minnesota Extension Forestry team. We present one of these seminars, webinars each month. Recordings of all of them are available online. I know we've got a good group tuned in, and I want to welcome everyone online as well as those of you here in St. Paul. And without too much further ado, I guess I have one or two quick announcements or things to mention. If you're in one of the rooms, like right here in St. Paul or another broadcast site around the state, we'll give you opportunities here in St. Paul. I'll just ask if anyone has any questions, you can relay that to me. Kenny is going to just pause a couple of times during the presentations to take questions. Those of you online, just go ahead and use the chat pod to submit your questions, and I will relay those to Kenny. So he won't be looking at his screen for questions. When he pauses, I will relay those questions to him. So again, online, don't wait for a pause. Just go ahead and put your questions in anytime on the chat pod. And without further ado, I'm very happy to welcome Kenny Blumenfeld. He's a climatologist with the state of Minnesota, DNR. His office is very near here on the St. Paul campus. And Kenny, you're on.
All right, great. Thanks, Eli. Thanks, everybody. It's good to be here. It's always interesting when there's a virtual audience, and then we got one in the room here too, but because I can't see the expressions on everyone's faces at their computer, but my guess is looks cool. Anyway, we're going to talk about the changing climatology, and I'm actually going to work into this a little bit of the asterisk that comes along with this season. All right, because this season, when you think about some of the talking points and main points that I'm going to share with you, this season is forcing us to make more explanations, but it hasn't really changed anything either. It's kind of interesting that way. I do get a lot of requests to share my presentations. I told Eli it's too big to share, but I have put this up online. There's a URL I can send Eli and Madison. Just ask. We'll have the vast majority of the content here. I did add a few slides at the last minute that aren't on the online version. All right, so when we talk about the changing climate, and by the way, this is about half of my job, is to do what I'm doing today. There are always some things to kind of bear in mind. One is that the climate news that we hear about, usually in the paper, if you're scientists, you might be reading about it in journals. And generally, scientists, practicing scientists, have a slightly better ability to kind of be reflexive about what they're learning about the climate. They understand nuance because nuance is part of the work that they do also. But in dealing with the general public, and really most people and non-professionalists even, there's a lot of conflation that happens. There's a lot of assuming that something I heard about in a different part of the world must be true here. And again, I work for the state of Minnesota. A big part of my job is helping people understand what's going on in Minnesota, specific to our climate. I'm not a forester. I'm not a hydrologist. I'm not an entomologist. So there's a lot of other impacts that are important to Minnesota that I can't necessarily speak to, other than smart people like those in this room or online have told me some things, or maybe have read a couple things. But my expertise is definitely in the climate. Another thing to keep in mind, there's two different branches of climate science, and that's a simplification. But we have the past climate that goes right up until right now, and that's all the climate that we can measure with instrumentation. And then we can summarize those measurements, those observations. We can summarize them through statistical analyses or through simple kind of baseball card style analyses too. Warmest day of the year, coldest night of the year, number of days with the precipitation of a certain threshold. That's all information you get from the observed existing climate, thanks to mostly volunteer human observers. Cloquet, for example, is one of our long-standing observers. It's great to have over 100 years of observation there, or nearly 100 years. Similar in the Grand Rapids Forest Research Lab, go back into the kind of 1920s or so, pretty comfortably. We can do the same at a lot of the extension offices around Minnesota, but those are just examples. We have citizen volunteer observers who've been at it for 3 generations also. That's kind of the backbone of what we can say about our past climate. Then you get into the future climate. There's no thermometer for that. There's no rain gauge for that. There's no instrumentation that you can look at and tell you what's going to happen in 35 years. And we don't really know with precision what's going to happen in 35 years. So we rely on increasingly sophisticated numerical simulations. These are the infamous climate models. So climate models, although they were pretty good at sort of guessing the temperature of the world 30 and 40 years ago and what the temperature of the world would be, they have always lacked spatial precision. And that's an area where we're getting better. So even though they were pretty good at understanding the global temperature is going to increase by an average of X per Y, they couldn't really tell you what that meant for Minnesota. But now computer models have the ability to be downscaled using physical techniques, meaning taking physical relationships that govern the atmosphere and actually rerunning the climate models over those physical relationships. The gist of all of this is that observations and projections are 2 different branches of the science, and where a lot of the people that I deal with are getting their information isn't from science, but it's from popular media, from an Atlantic Monthly article, or the New York Times, or Fox News, or wherever. And a lot of times, once you're at that level of information, think about what you read in those situations or what you're hearing on the 3-minute news report. They often don't mention observations or projections. They just say the climate. And it's in that situation that it starts to be confusing. Are we talking about future climate, or are we talking about something we've already observed? All I'm saying is keep in mind these are different. I'm going to try and be clear about which one I'm talking about. Big one, variability and trends. We have them at the same time. Minnesota has cold winters, warm summers. We also tend to be snowy during the winter, and we tend to be wet during the summer. But we all know that sometimes our winters are colder than we're used to, and sometimes they're warmer than we're used to. Sometimes our summers are hotter, or wetter, or cooler, or drier. That's variability. That's always been there, and it always will be. However, we also have ongoing trends. We're getting warmer. Most of the state is getting wetter. We're seeing an erosion of winter. These are facts that are part of the observed climate, and they don't negate the variability. The variability doesn't disprove the trend. We're having suddenly winter has arrived. We had some extreme cold a couple weeks ago that we honestly hadn't observed in this state for a couple decades. That doesn't change the pervasive trend. It doesn't change the ongoing trend. It tells us, hey, we can still get old-fashioned style variability, which is actually, when you look at some of the slides I'm going to show, you might find it a little bit comforting, even if it was miserable. They don't disprove each other. This is the most common source of, for example, a tweet coming from someone from fairly high power and authority, or disagreements that people might have around the dinner table about the topic of climate change. It usually gets into some kind of either misunderstanding or abuse of the distinction between variability, which is built into our climate, and trends, which are also to an extent built into our climate, but we know the majority of the trends that we're talking about are to be human caused in the recent decades. In Minnesota, I deal with a lot of people, and this is actually really important, especially rhetorically. There are a lot of people who actually believe that everything's getting worse. And then there are also a lot of people who believe that people are trying to tell them that everything is getting worse. And the fact is we have a lot of hazards that are built into our climate. They're not all worsening. there's no guarantee that climate change makes everything worse. And I have found this is really useful for calming down some people who we've already got our hands full, to be quite honest. We already do. If you just focus on what the facts are, we've already got our hands full. We don't need to make it worse by being sort of hypochondriac about the weather. And on the other hand, it's also helped some people come from maybe unflinching positions to say, look, I'm not telling you that everything's getting worse here. They're still hazardous, and we still need to manage our resources as if those hazards will always be there, irrespective of whether they're changing. Now let's focus on the ones that are. And then the last thing is, this changes. Not just the climate, but of course science. Science, fortunately, it moves forward. It does put the burden on us to stay up to date. All right, let's talk about what's happening. Well, here's an example of variability and trends working together. Here's the upper Midwest: Minnesota, Wisconsin, Iowa, Michigan. Average annual temperature. I don't want you to focus too much. How did he do that? This is just done at the National Center for Environmental Information. It's a regional homogenization. Basically take a grid of data, take all of the temperature data from all of those grid cells, and just mash them into one average over that area. Then you get the average temperature per year. And we're taking it from 1895 through, that goes to 2017, I believe. Your eyes will tell you probably everything that I'm about to show you anyway. You can see the variability, and you can probably also see a trend, but let's point it out. Here's how we commonly express a trend as a linear trend based on ordinary least squares regression. It's quite frankly the easiest and also the least, doesn't contain a lot, it misses out on the variability, but it's a nice, simple statistical summary. And this tells us that over this period of observation, we've got a 0.19, this is equivalent to about a 0.1 degrees Celsius or 0.19 degrees Fahrenheit increase in temperature per decade. So over this 120 plus year period, you'd expect that to, you can basically multiply that trend by about 10 or so, 12. That gives you the total temperature change on average. But we know more than that trend. We've got periods. You can actually use statistical techniques to find breakpoints. I try not to focus on that too much when I'm doing public outreach, but there's obviously, you can go deeper. And we see that the first part of that record, and by the way, 1970 is a common inflection point. You might see some studies using the 80s or the 90s, depending on what they're looking at. But when you look at temperature around the globe, in North America, ocean, surfaces, locally, regionally, everything starts to snap upwards. Within a few years of 1970. It's really interesting. And so we're going to use that as a breakpoint commonly here. You see, before that period, the trend is shallower. It's on the order a little over, around 3/4 of a degree. I'm sorry, 0.075 degrees Celsius per decade, or about 0.12 of a degree Fahrenheit per decade. But look at after 1970. Now we've got a trend, temperature increase, and this is around the region, and we're not even looking at times of year or specific parts of the region. We're just taking that whole 4-state region and homogenizing it, and the trend is 4.5 times faster since 1970 versus that whole period before 1970. So we see that, but we also see built into that trend, look, we have cold years and we have warm years. They don't work only in isolation. You get groups of them also. We know this. We intuit it, but then we easily forget it, especially in heated debates. Variability is there right alongside the trend, and of course we could go backwards and see it was always there too. So it's part of our climate. And I just want to say, I'm not sanctimonious here. Even climatologists can get caught up. In fact, I'm going to give you this presentation, and I can tell you that one of the things I'm always concerned about is that some moment of variability is going to come by and convince everybody that I was wrong. Like we're going to get a super hot summer or a really cold winter, and everyone's going to go, this guy's, he's a crackpot. When actually we're talking about something that's really based on longer term. All right, Minnesota's getting, here's the three things. If you want to be smart about Minnesota's climate, just three things you can say. We're getting warmer and wetter. We've seen a stepwise shift. And that's also projected to continue. I'll be moving back. So it's okay. The lowest temperatures, think of winter time, think of nights, think of winter nights especially, and think of the coldest times of winter. That's where we're seeing the fastest increase. There's been a rapid loss in cold extremes. Of course, we do still have variability, and that is projected to continue. And the third piece is that extreme rainfall. In terms of the frequency of events and the magnitude of those events, those are both increasing. All right, here's some important hazards that aren't changing in Minnesota. And again, I'm talking about Minnesota. We'd have a very different conversation here if we were talking about California, which is seeing much more climate volatility than the Midwestern part of the country. If we were talking about the South, the Deep South, we would have a different story. Minnesota's story is fairly unique to Minnesota and the region in which it's embedded. And in our region, there is no evidence of an increase in what most people associate first with climate change. Because climate change, of course, used to be what? It used to be global warming. And if you step back, the whole reason we talk about this is because the global temperature is indeed increasing. The global temperature is going up, not quite year by year, but certainly decade by decade, which is why you keep hearing, last year was the fourth warmest on record. Well, how come every year seems like it's the fourth warmest on record? It's because we're really warming on an almost decade by decade, decade over decade pattern right now. So most people hear warming and they assume hot. Makes sense. But there's two ways to make a room warmer. You could crank up the heat. You could also snuff out all of the drafts. All right, and right now in Minnesota, that's basically how we've been getting warmer, is not through hot days, not through more warm nights, not through heat waves by any measure. We haven't seen those increasing. Projections indicate, however, they will. Give us a couple of decades yet. Seems like the science indicates we might have 2 or even 3 decades before the heat waves really kick in. But this is not an area where I'm going to tell you to bet on, because we are in a changing climate pattern. But right now, there's no evidence that we're heading towards worse summer heat. Drought in Minnesota. When you see how much wetter we're getting, you'll say, oh, I see. We're not seeing increases in drought. Every year we get nervous. Are we going to start seeing it? We haven't. We're in a wettening pattern. And the last one is just interesting, and I always do hear from foresters about blowdowns and the wind throw events. We all know that we have limited data, not just from forestry, but from all of the conventional severe weather data collection methods. But when we do our best and we try our hardest, we don't see any actual increase in the severity of tornadoes, which are the #1 kind of severe weather hazard, because they're discrete and they're powerful. They're not increasing in number, at least the ones that really matter. And I'll show you some evidence for that. And that's actually a national trend. In Minnesota, I do not want to jinx this because we'll have to come out of it, but we're actually in quite a significant tornado drought. We have not had a major tornado in Minnesota that's rated F3 or greater since the year 2010. And we could go all the way back through the record, even into the 1800s, when we didn't have a weather service and we didn't have radar, and we didn't have spotters, and we still don't see a period without those kinds of tornadoes as long as this one. So that's unusual. But so these are 3 really important families of hazards that are not showing any change. And there's no smoking gun pointing towards them getting worse. we see some uncertainty with the future in drought and severe convective weather. I do want to mention, it's going to be hard for us to get out of this century without getting hot. That's just the physics are on the side. Eventually, you're going to get hotter, and we can walk through some of that. I don't want to I could spend the rest of the hour on this set of slides, but this is basically a re-summarization of what I just said. Our scientific confidence of these common weather hazards, that the changing climate is actually influencing them, starts out at the highest level for the loss of winter as defined by extremes of cold, and for increases in heavy and extreme rainfall. There's the highest level of scientific confidence that those two changes that we're observing have a link to our changing climate. Everything else has low or the lowest levels of, heavy snow is currently having a pretty good, a nice little renaissance in Minnesota. Even as winter shrinks, we're seeing heavy snowfalls increase, but it's not necessarily being reflected by snow depth or the duration of snow on the ground. It's just you're getting more events that are what we think of as heavy. We have the lowest level of confidence that heat waves and drought have worsened with climate change in Minnesota because they're not showing any signs of worsening at all. So how could we blame that sort of non-worsening on the changing climate? That was what we've observed. Now when we look at what we expect based on the best available science, it's a different picture. You do see winter extreme colds and extreme rainfall continuing their high level confidence rankings in terms of being linked to the changing climate. But heat will kick up in there, and then drought, slightly lower in confidence, but drought would follow the heat, because if you get more extremes of heat in summer, you're going to be removing more water from everything. You're going to have this desiccation, and drought does tend to build on itself, and so you could at least have flash drought, if not persistent long-term drought. And again, this is part of our climate. The fact that it's not worsening doesn't mean we don't have to worry about it. It just means, it's still going to be part of our climate with a regular recurrence, and we haven't seen a change in that recurrence. But once heat gets worse in the future, then our droughts are going to they're going to just have a little more to them. And we don't really know what's going to happen. I can't tell you what's going to happen with tornadoes. It's one of the more exciting areas of scientific research on the changing climate. I'm sad to report there's actually not a lot going on from the people who could be doing really exciting stuff. It requires a lot of supercomputing, a lot of dynamical downscaling. All right, let's just look at how we've gotten warmer and wetter. We're taking the state of Minnesota, we're taking all of it's again a grid of data, and you just take the spatial average around Minnesota. This is annual temperature. So this doesn't tell you much about any one point in any given part of the year. It just tells you that around the state, the average temperature is 40 degrees Fahrenheit. That's a few degrees, a couple degrees Celsius. And the average precipitation is about 26 inches annually. All right. And what we have here is all these dots are just the years. Any given year's combined temperature and precipitation, and these are the 20th century averages in the middle. It's nice and symmetrical. These would be warm and wet years in the upper right, and we'd have cooler and drier years in the lower left. What I haven't done, I've excluded everything after 1986. So you don't know what 1987 through 2017 looks like. So those 31 years, we don't have them. What happens when we add them? Watch. I feel like whenever I do this, I go back, I feel like I'm doing the JFK replay, but up and to the right. Up and to the right, we are more frequently in the upper right quadrant of the temperature and precipitation distribution, meaning more warm and wet years. 2016, not the very warmest, not the very wettest, it's up here, was the combined warmest and wettest on record. And everything that it had beaten out was also from those most recent 31 years. 2017 is right in here. 2018 is nearby. We didn't add it because the shutdown prevented the federal government from producing the the December data, which was required to compute the annual totals. I could probably update that now, but we know it's in here somewhere. So that's the kind of jump. We just jumped into a different sort of hydroclimatic regime. Here's an example of how we've been getting wetter. This is in the Cottonwood River watershed. We've got data from Lamberton here from 1962 through 1982, and this is just precipitation during, basically during the July through June period. If we then add from 1983 to 2018, that is if you use a t-test to ask if these are the same distribution, it fails at every confidence level you would ever assign. These are different precipitation regimes. You can kind of zoom in and see it. The difference over this period is in the Cottonwood River watershed, its average is about 3.5 inches of rain per year. Now, that's hard for most people to grasp. What is 3.5 inches of rain? In a rain gauge, it's this much. It's this much, people online. But what that means is that's about, if you just average that 3.5 inches over a square mile, that'll give you 60 million gallons. Okay, so that's 60 million gallons per square mile of extra rain coming out of the sky. How many square miles in Minnesota? 84,000. There's about 1,000 in that Cottonwood River watershed. So it's a lot of water that is being made available to the land. Got a question?
We've got a couple of questions online. Do you want to, is this a good time to pause? Or?
Stop me, sure.
All right, so we've got 3 good questions that have come in from Cloquet and Duluth. Let's go with the middle one first. You've used terms like increasing and changing. Can you speak a bit about the baseline to which you're measuring changes and any limitations we should be aware of?
That's a great question from a smart person. It depends. So back here, we're talking about the simple change versus 20th century averages. So 20th century averages are one way of averaging the climate considered to be pretty stable. Obviously, we've got a smaller period now since the 20th century ended. So the limitation of that would be, it's not quite apples to apples. We've got a fairly large sample in the past versus a small but growing sample present. So that would be one example. Here, I'm actually just doing period to period change, and these are both relatively short periods. So statistically, some of the limitations would be, and this is just as far back as that particular station goes, but the limitations would have to do with the same limitations when you do relatively small sample comparisons and statistics. You know, one is outliers might have an outsized influence on any part of the distribution, and you're just going to have error propagation until you get to, you know, I think what I'm trying to do is assemble a story. All of the data sources that we're going to use have some limitations, but when you have enough of them, you assemble a story that gives you the larger picture. And sure, even with the limitations of this data set, we see a corroborating story with this data set that has fewer limitations. So that's a great question.
Yeah, another interesting one. What about ice storms? Paul Huttner has suggested that they are becoming more common, and I'm seeing more ice storms up north. This question's from Cloquet, but is it statistically significant?
That's a great question. So we've looked at it a little bit. What we are seeing is more rain in winter events. I don't know if it's statistically significant. And again, when we say more, we're saying let's establish kind of randomly some baseline period. So we take whatever data we have. There's a clear visual increase in the number of rain during winter events, including in the Duluth area. I haven't looked at Cloquet specifically. Ice storms are a different animal. And so when we think of ice storms, we're talking about ice bringing down tree limbs and power. And those are regional disasters, if not catastrophes. And what we're seeing more of, and we know that people are reporting more, are slippery days, where you get rain and it freezes. It's not destroying the infrastructure and it's not breaking things. other than but it becomes a traffic and a slip and fall hazard. It's one of the things we're wondering about, and we're looking to join forces with some other climate scientists and get some answers. It's another very good question.
Great. We've got one more here. Oh, a couple more now online.
Let's do this one, and then let's hold that last one.
All right. And are there any questions here in St. Paul? Quick one?
Well, the increase of rain is kind of speaks more to supporting buffers, the state program for buffering.
Did you say buffers? Hey, everybody, you've been great. I got to go.
Yeah. All right, Kenny, let me throw one more at you. Don't you need to account for the shift in the North Atlantic Oscillation into the positive phase during the 90s and 2000s?
I'm just doing straight climate analysis here. We could also do the Pacific Decadal Oscillation and some of these other indices. If we wanted to do a deep analysis, I think, sure, those things would be important, but we're just looking at what's in the actual climate data right now. I'm not trying to attribute them to larger circulation changes. Do things like the North Atlantic Oscillation or the Arctic Oscillation or the Pacific North American pattern, do these teleconnection type issues modulate the climate that we experience? They definitely do, but it's beyond the scope of what I'm doing to try and account for them. So when we talk about how we're getting wetter, we looked at some of that. We're seeing increased frequencies in heavy rainfall and the magnitude of the heaviest rainfall. And then we're seeing this winter warming and the loss of cold extremes. And we're kind of going to drill into those for most of the rest of the time. All right, so this is a really neat data set that we have. This includes Cloquet, and it includes 40 stations in Minnesota, although I believe I've had to decommission one of them if I want to bring this all the way up to date, because it's no longer a long-term observing site because it's not observing anymore. But we take a census of these 40 long-term stations that have 100, or in this case, I think it's 101 years of record. And we just ask those 40 stations, how many daily 1-inch rainfalls did you get? You know, and we're not literally asking stations that, we're doing this in a database, but how many 1-inch rainfalls were recorded in a day? And then we just take the sum of those. So each of these bars represents the number of sort of station days per year with 1-inch rainfall. And again, we have not changed the playing field. There's only 40 stations included throughout this record. And we see it. I mean, visually, you can see the increase. And you can look at it a number of ways. You could draw an arbitrary threshold and say, well, how many times do we have 200 station days? That's clearly increased over recent decades. I do always caution people, this period here, we are in the drought of the 1930s. So it's not entirely unusual that we'd see fewer heavy rainfall events during that period. But the fact is that even if we exclude that, the increase continues even after we come out of the drought. And we could even look at, 2 years with 250 of those station days reporting an inch of rainfall or more. So this is an inch of rainfall isn't a big deal. Most of the time, it's not going to cause flooding. If you've already been wet, you might see minor problems. But it's sort of a good entry-level kind of heavy rainfall event. It's going to cause softball games to be canceled and things like that. If we look at 2-inch rainfalls, these, we're going to step up to higher and higher consequence here. 2-inch rainfalls, again, don't worry too much about the 1930s, but you do see an increase even after that point. Not just in the spikes, but in the overall mass. If you were to fold over the right over the left side of the graph, there's just more mass on that right side of the graph. So we're seeing more 2-inch rainfalls. Now 2 inches, if you've been wet, that could be problems. You're going to see streams rising, possibly out of their banks. You're going to see, a lot of standing water in fields and in forests. And 3-inch rainfalls, now you're kind of at the entry level of a pretty major event. You only get one in the southern part of the state every 5 years or so, and maybe in the northern part of the state every 7 or 8 years on average. But these have increased in frequency also You see 2016 standing out as a very wet year. Let's not over-focus on it. It's perhaps just a moment of variability. I know if we added 2017 to this one, we're in 4-inch rainfalls now, it would be back down here. In 2018 is kind of, it's high, but nowhere near where 2016 was. But you do see an increase. We're getting more. And when you have 4 inches of rain, you're going to have flooding. You're going to have streams over their banks. You're going to have flooded low-lying areas and intersections and things like that. And of course, we could just take all 40 of these stations and just ask, what's the largest rainfall each year in all of 40 stations? And what's interesting to me is if I follow along the bottom, I don't see a huge change, meaning a lot of years are kind of like they've always been. The biggest rainfall of those 40 stations is, somewhere between 3 and 4 inches maybe. And, maybe that's a slight increase over what it was like at the beginning of this record. Where we actually see the changes is up here. Look at when 8-inch rainfalls became more common. And we've started seeing rainfalls that we just never used to have. And again, this is just a sample of 40 stations, but they have nice long records. It's safe to say Minnesota has begun seeing rainfall of the sort that it just had not seen in its observed record up until the last few decades. These have become more common. The Minnesota statewide record is actually from one of the stations that doesn't have 100 years of observation, but it's 15 inches. It was set in 2007, so that'll be up here somewhere. We've had some wet years recently. 2018, so in 2016, at the Waseca Extension Office, they broke the statewide precipitation record with 56 inches and change. In 2000, we thought that was such an obliteration of the old statewide precipitation record, we figured that was safe for a while. Well, this year, Caledonia broke it. And then we found out on delay that Harmony, which was reporting its data a little bit later because they actually send in physical forms, they actually broke the Caledonia record. So we had 2 stations that broke the current precipitation record, and I believe Harmony came in with over 60 inches. A lot of rain. We never thought we'd see a 60-inch rainfall year in Minnesota. That's like what you get around the Gulf Coast. Obviously, the consequences, before and after, they definitely got the kids off of the field before that happened, so you don't need to worry about their safety. Here's Brewery Creek and Duluth before and after. And this is all kind of, this is eye candy. We know what extreme rainfall does. And I try and caution people. Every place in Minnesota is not getting wetter and worse rainstorms every single year. That would not be accurate. It's not accurate to say that you're going to see record rainfall wherever you live for sure in the next X number of years. That's not how we look at it. Extreme rainfall will continue to be isolated and somewhat, spatially isolated and also temporally isolated in time. Rare events. But what it does tell us is if we just look at the whole state, scenes like this will be more common. And not because we're out documenting it better, just because they're becoming more common. They're still going to be isolated, they're still going to be rare, but we're going to see more. We've been seeing more. It's already happening. This is going to continue. And even if we go through periods that are drier than we are now, the general trend is expected to be upward. And the models, the best models that we have access to, tell us, yes, if you look at the heaviest couple of days of rain in the year, the 98th percentile rainfall events, we'd expect, an additional day or so of that caliber of rainfall per year. Doesn't mean an 8-inch rainfall everywhere. Just means, in a typical year, your biggest rainfall is going to be somewhere between 2 and 4 inches. And your second biggest rainfall is going to be between 1.5 and 3 inches. And we're going to add one somewhere in between those, an extra day like that. That's what this is telling us. And we've already started to see it, so it shouldn't be surprising. When we think of how we're warming, this is the real sort of subtlety of our changing climate is that summer is warming. Since 1895, it's warming at a rate of about a little over 1/10 of a degree Fahrenheit per decade. And since 1970, it's warming at a rate of a little less than 1/10 of a degree Fahrenheit per decade. So summer is warming, but winter's warming faster. The long-term rate was about 3 times what summer's long-term rate was. And since 1970, it's more than 10 times the warming that we're seeing in summer. So I would say winter in Minnesota is warming. You're safe to say 10 times faster. This is 13 times faster. But since one of the people online asked a good question about limitations, the limitation of this comparison is it's based on just the differences in the linear trend or the linear rates of increase. And that means linear analyses are always really susceptible to what the next member added to the series is. So as we add another year, these rates can go up or down and change that difference. But Minnesota's rate of warming right now, and over the last 5 decades or so, is 5 times or 10 times greater in winter versus summer. And we can look at how it's changing. Like if we look at the winter low temperatures, again, averaged around the state, going back to 1895, we do see this long-term winter low temperature. So that's take your 90 days of winter, you average the lowest temperature at each station, and then you average all of those stations. And you just look at the trend. It's actually a pretty sharp trend. It's almost 1/2 degree Fahrenheit per decade of warming all the way back to 1895. But you really see what's happening in the last few decades. If we kind of focus on them, the low temperatures during winter in those decades were what would have previously been the warmest on record. Those years. We've got a whole bunch of those years. Look at all of them. And we won't be adding this year to that oval. That's all of that is. We know that. This goes through last winter. Last winter was a little bit colder than the long-term trend. So we see that. But look at, a lot of people thought last winter was cold, but look at actually, if you stare at that dot and then look left, look at how common that kind of winter has been. You will be similarly unimpressed with where this winter finishes. Okay, did that already. And we can look at things like freeze-free characteristics, where if we just look at the number of days where the temperature remains above freezing, and we go to a rural site like Milan out in west central Minnesota, I think it's Swift or Chippewa counties. It's one of these volunteer cooperative observing sites with multiple generations of observers. It's one of the best in the country. They've seen this huge uptick in the number of days per year where the temperature doesn't fall to freezing temperatures or lower. And right here, what we're tracing with this line graph is just the average number of days between the last freeze of spring and the first freeze of fall. You hear this notion that growing season is expanding, right? I think this is important for foresters. And we do see in the last few decades that growing season is expanding. But if you look backwards, and we see this also, the 1960s had long growing seasons in Minnesota, but they didn't have a lot of days outside of the growing season that were also really warm, keeping the temperature. It was sort of binary. You kind of had a growing season and you had the rest of the year. Now what we see is the growing season's only slightly longer than it was in the 60s. So yes, it is growing, but it's this proliferation of days outside of the growing season that are also above freezing. So maybe you have your first freeze of first freeze of autumn, and you are cold for a few days, and then you back up above freezing for another week. Or maybe you go into November and the temperature has several days above freezing. This is the kind of change in the growing season characteristics that we're seeing across the state. Milan is just one example. It is Milan. It's not Milan. I know we all think it's Milan. It's Milan. If you go to Milan and you say, I'm happy to be here in Milan, don't. And if we look at how winter is changing, we stay in Milan here. Just look at the highest highs of winter. You do think, oh yeah, I do remember a lot of warm winters. And I think we assume that that's the warm days we've experienced. But if we look at the highest high temperatures in winter, there's not a huge change across time. I mean, and down here we've got the 15 warmest days of winter, and there's not a huge change. That's not where we're seeing it. What we are seeing instead is a change in the lowest lows of winter. So I have not added whatever Milan recorded during the last cold spell here, we'll see. But there's been this general trend that's been on the order of about 18 degrees Fahrenheit per century increase in the temperature on the coldest day of the year. So if you look at the coldest temperatures recorded recently, look at what Luther Opjordan thinks is cold. And then just look left and look at how common that used to be for his grandpa. And look at what grandpa used to record that Luther and even Luther's dad didn't. So we did get pretty cold recently, but it had been a generation, a whole generation of people hadn't really seen anything like that, and it only lasted a couple days. We can do the same thing at Cloquet, lowest lows of winter. I did add, I know we had a negative 37 at Cloquet. It's cold. It doesn't really stand out historically. That's what we got at the coldest moment of this cold snap, was a negative 37. I'm not going to poo-poo it. And I'm not going to say we'll never be cold again. But the best that we got now was something that used to be pretty common historically. And that is becoming less common. We can look at the minimum temperatures. How many times do they fall to negative 35 at the Grand Rapids Forest Research Lab? I've been told that this is an important number for the eastern larch beetle. Keeps it at bay. I can't confirm that, but it's easy to count the number of days that fall above or below any particular temperature threshold. And you can see that those negative 35 conditions used to be pretty common, and they've really fallen off a cliff. And I'm not sure Grand Rapids, I don't think, was staffed during the shutdown. So I don't know what they recorded when it was some of the coldest, but maybe they've added one or two, but we haven't had as many this decade or last decade as we used to have. And we can look at the cold nights and cold days by decade in Cloquet and just look at the average number of lows that are negative 25 or lower, and they've just been meandering downward. Not decade over decade, but the general trend is downward. And then in these light blue bars, let's look at the number of days where the high temperature remains 0 Fahrenheit or lower. And those have also meandered downward. We're just, not always falling off a cliff. Sometimes it's a general trend. Here's a graphic that's gotten some attention because it was used by scientists in some of the legislative hearings recently. But this is not to say that Duluth won't ever have a 10-degree Fahrenheit average temperature during the day, and that's ridiculous. We take the average season where you'd expect, the daily temperature to average 10 degrees Fahrenheit or less. This math shows us the depth of that season. Generally, in the 1950s, 60s, and 70s, from 1959 through 78, from right around Christmas to the first week or so in February, not every single day, but this was the season where the average temperature, the average daily temperature was, that's the high and the low average together, was 10 degrees Fahrenheit or colder. So the bigger the mass, the more below that threshold it is. I know it's harder to, once you start thinking about it, it becomes a little counterintuitive. When we add the next 20 years, you can see it had already taken a pretty good hit. And these are up out of the city, up by the airport. This is not a super urban area. And we can see that we had lost a week or a few days on the beginning and a few days on the end for a total of about a week. And a lot of that mass disappeared. And all this next piece means when we add the most recent 20 winters, right through last winter, you don't see a 10-degree season anymore in Duluth. It does not mean that Duluth won't ever get to 20 degrees or 10 degrees. It just means that the average over that 20-year period was that there were no periods where you had the average daily temperature of 10 degrees once you average in all of those years. Sure, any given year you expect lots of days where the average temperature is 10 degrees Fahrenheit or colder, but there's enough days where it's not, that there's no longer that 10-degree season insofar as the 20-year period is enough for climatology. You'd have to actually cheat and change the axes of the graph to find it, and that makes it more of like an 11-degree season, and that's not what we were after. So we've lost these sort of important elements, and I use Duluth because it's kind of the capital of winter. We could also look at ice duration on Minnesota lakes. We have a lot of ice out data. We don't have as much ice in data. There was some DNR analysis that showed basically over the last 3 decades, we've lost an average of 4.2 days per decade on the lakes in Minnesota of ice cover. So from the period between the ice in and the ice out has shrunk by about 12 and a half days on average over the last 30 years. Meanwhile, we look at the high temperatures during summer, and we don't see that same pattern. We don't see a big increase. So these are not just the warmest temperatures of the year, but this is the average daily high temperature over the 92 days of summer, June, July, and August, averaged around the state. The 1930s were exceptionally hot during the summer. We were in a drought, and so it's very easy to get both hot and then cold in the winter. And we only see 1988 standing out here. Nothing else shows us an upward trend. There's no trend line, there's no linear trend, there's nothing. Here was a hot summer in 2018, and look at where it stands. Or we can look at 2012, which was legitimately hot, and we also see, looking backwards, it wasn't standalone hot, it was just plain old hot. And there's no indication right now that we were having more of those. And when we look at the highest highs of Milan, again, even if you exclude the 1930s, which I'm all for doing that. I mean, if you're really dead set on finding something, you're still not going to. There's nothing that tells us we've left the historical ranges in terms of high temperatures, the hottest days of the year in Milan or in Cloquet. This gets us right through last summer. 92 was, I think, the highest last summer. Nothing unusual. If we count the number of 90-degree days in Duluth, this would matter because a lot of people, especially folks with fewer means, they don't have air conditioning. We've got a nice lake to take care of that. If these numbers were going up, we might have a bigger problem. But right now, we're not seeing that. We're not seeing any tendency towards leaving historical ranges yet. But the models do tell us, the same ones that showed us we're going to be getting wetter, they tell us, well, we're going to warm winter so much. I mean, it's warming so fast that you're going to start spring and then summer at this higher baseline. Then when you add in a normal amount of summertime heat on top of that, already warmer baseline, already warmer starting conditions, add in the normal amount of summer southerly winds, it's going to be easier to hit 90 and 95. And especially the southern and western parts of Minnesota should see several days by the time we get to the middle of the century with those kind of extremes of heat. Just quickly, we're not getting drier by any hydrological, climatological, or meteorological indication. However, I think foresters are always quick to point out, tell that to the trees, where temperatures are rising very quickly in northern Minnesota. And so we're seeing, you can call it hydrothermal deficit, you can call it drought-like symptoms, even though northeast Minnesota is getting wetter on average. It's also getting warmer, and it's a combination of factors that are causing increased mortality and illness among trees in northern Minnesota. We do not have a drought smoking gun in the future in our region. Farther south, we do. This is just the longest dry spell of the year. How much longer does it become? Between 0 and 1 day longer. That is not a smoking gun, but remember, it is going to be getting hotter eventually. This is 2040, 2050. We don't know exactly when that would begin, but then we'd be at least prone to more flash drought and severe drying as a result. But until then, we should just accept that drought's part of our climatology. And the last one we'll hit on here is, these are the F2 tornadoes in Minnesota. We can push it back farther using less standardized data, but we don't see any trend towards more of these damaging tornadoes. And these are the ones that like take down the majority of a house. So they do substantial damage. We know we're better at seeing the ones that don't damage anything. Storm chasing and mobile phones and things like that have made it easier. But the tornadoes of consequence haven't really changed in frequency. They haven't increased, even though we're better at detecting them than we've ever been. So if we just summarize that, we've gotten wetter and warmer. We've seen a big shift. That's expected to continue. The wetness has been driven by more frequent and larger heavy rainfall events. That's expected to continue. And it's the coldest conditions that have eroded the fastest. Hot weather hasn't worsened. We think it will in the next few decades, but we don't know exactly when that'll start. Drought, we don't really know. We see some symptoms for drought now, but it mostly has to do with temperature, extreme warming. And even though there's an increase in precipitation in northern Minnesota, the trees are undergoing hydrothermal stress. And we haven't seen any change in tornadoes or other severe convective weather hazards. So that's what I got.
Awesome. We do have a few questions online. Why don't we take one from here? Go ahead, Dave.
What about straight line winds, derechos? I mean, you say convective storms. They're not, I don't think, are they?
They are, yeah. So the question for folks online was, what about derechos, straight line winds? Those are convective storms. They come usually from lines. So what we used to call squall lines, certain arrangements of thunderstorms that propagate forward, they accelerate. They often will harness a lot of intense winds a lot. We don't have a great data set on them. When we have looked at what foresters have provided with us, there is actually no indication that we're moving off the charts there. I was actually surprised. 2016 was exceptionally busy in Minnesota, in northern Minnesota, for those kinds of, they might not have been derechos that have a specific definition, but there was a lot of power outages and tree damage in the summer of 2016, and it actually doesn't really stand out historically. We just got our attention. I think we pay more attention. I do hear from foresters that they think it's windier in general, and when I ask them what they mean, they often say it's gustier, and that's something we kind of need to look into. But it's not necessarily straightforward to do that. But there is no indication right now that we've seen more or worse derechos in straight line wind events. Where Minnesota is closer to what you might think of as derecho or a straight line wind alley than it is to tornado alley. So we're kind of on the northern and northeast of the main tornado alley, but we're kind of in the heart of the larger straight line wind belt. And so we do go through these years when we have multiple events, but that's also something that we've always had.
We do have a couple other questions online. Have you looked at seasonal Mann-Kendall tests, for example, monthly, or I think you'd call these meteorological winter, December, January, February, March, April, May, and so on?
For temperature or precipitation?
Oh, I'm not sure.
Yeah, I mean, so if I'm doing research, and I should mention, I don't do scientific research in my current capacity. My job is really I'd love to do some research, but my job is mostly to interpret the science and then give it back to the public. So I'm not right now in a statistical analysis capacity. So most of what I do has to be digestible by the public. Yeah, we have played around with more robust statistical techniques. And so if we're doing, and you need something that's non-parametric for a lot of the things that we look at, like when we're looking at counts of days, for example, because you don't have actual data, you're just counting something. Most of the things that make the top three, the lists of things that are changing, we could find a good number of statistically significant outcomes from a variety of tests, whether they're parametric or non-parametric. And moreover, there's a lot of literature in support of it. Once we get into things like drought, tornadoes, heat waves in Minnesota, that's where we really start failing to reject null hypotheses and lacking any kind of statistical significance. And so it kind of depends on what we're after, but yeah, for a number of things we've done a variety of, whether it's Mann-Kendall or t-tests or just linear trend analysis or breakpoint analysis, yes, but we don't generally go too far with it because most of my audiences are what I think of as intelligent lay, and they don't need the statistics.
So we've got a couple of other, first one's really quick. Someone's wondering if you would show the first summary slide again. That's kind of opening ideas to keep in mind, I think is what you called it.
Well, if they can just let you know if we're.
Yep, and you mentioned that you have a link that you'll share with us since you offered that. Yep, we will, I'll tell folks, anyone who registered, we will put it in an email to you and we'll also add that link to the.
It might not have the cloquet specific slides in it. We're almost there. There's a lot of slides. You guys are very patient. That's clear. Was it this one? Ask if it was this one. Or was it?
No, I think you want to keep going. I think it was kind of ideas to keep in mind or something like that at the beginning. It was about trends and right there. I hope that's the right one. Whoever requested that, let us know if you had a different slide in mind. And Kenny, one other question, and then I think we'll break. Of course, folks here can still ask questions locally. Is there a tool to predict Midwest rainfall and temperature into the future? This person's asking for a simple tool that a layperson could use.
I want that too.
Yeah.
That's a great question. I want it too, but so no, but there might be hope. There's been a lot of good modeling work done at the University of Minnesota in support of some other research projects, and we might be able to piggyback on some of the data. Now, those right now we have really cool options for summarizing past data, but understanding the future has been sort of a holy grail, especially because a lot of the resources to do it are kind of fall victim to some of what I described earlier, which is that they're based on these large global model simulations that were accurate at the global level, but they start to lose meaning for Minnesota. And even some of the treatments that have been applied to them don't necessarily jive real well with the climate that we have here. And then the third kind of, I don't know if I said two things, but the third thing, another problem with that anyway, is also just that access is pretty difficult. You have to often take in arcane data formats. So what we do have potential access to high quality Minnesota specific climate projection data that will be summarizable in terms of daily or monthly and annual precipitation. And at least be able to provide a range of projections or sort of a modified climate graph at kind of a click and point, or point and click and extract pretty simple user interface. And we're hoping that would be accomplished within a year. I mean, the project isn't live yet, but that's what we're hoping for.
Great. I think with that, we're a few minutes over time. I'm going to call a close. We have applause from Duluth, the capital of winter, they said.
Capital of winter.
Kenny. So those of you online, I just want to draw your attention to the chat pod. If you are interested in requesting continuing education credits, you do need to fill out a form online. The link is right there in the chat pod. Those of you at a broadcast site, if you would like continuing ed credits, you should look for a sign-in sheet, or if you're in St. Paul, talk to me because I didn't put it out. Kenny Blumenfeld, thank you again very much.
Of course. Thanks, guys.